Welcome to this coding tutorial. In this session, we'll be tackling LeetCode problem number 559, maximum depth of N-ary tree. This is a fundamental problem that helps you understand tree traversal techniques and recursion in depth. Let's dive in and explore the solution step by step. In this problem, you are tasked with finding the maximum depth of an N-ary tree. The maximum depth is defined as the longest path from the root node to the farthest leaf node. To clarify, a leaf node is a node that does not have any children. For the input, we are given the root node of an N-ary tree. This tree is represented using a class called node, which has two properties: val, an integer representing the value of the node, and children, which is a list of child nodes. If the node is a leaf, this list will be empty. The output should be an integer, which represents the maximum depth of the tree. The problem will become clearer as we look at some examples. Let's take a look at our first example. Here, we have an N-ary tree with the root node labeled 1. This root has 3 children, nodes 3, 2, and 4. Node 3 further has 2 children, 5 and 6, while nodes 2, 4, 5, and 6 do not have any children, making them leaf nodes. The task is to determine the maximum depth of this tree. The longest path from the root to a leaf goes through nodes 1, 3, and then either 5 or 6. This path consists of 3 nodes, so the maximum depth of the tree is 3. Now consider a different example. In this tree, the root node, 1, has only one child, node 2. Node 2, in turn, has one child, node 3, and this pattern continues until node 5, which is the only leaf node. Here, there is only one path from the root to the leaf, which traverses nodes 1, 2, 3, 4, and 5. This path includes 5 nodes, so the maximum depth of the tree is 5. Notice how this example illustrates a tree that is essentially a straight line, demonstrating an edge case where the depth is equal to the number of nodes. In another example, we have a tree where the root node, 1, has 3 children, nodes 2, 3, and 4. None of these child nodes have any further children, making them all leaf nodes. In this case, the longest path from the root to a leaf includes just 2 nodes, the root and one of its children. Therefore, the maximum depth of the tree is 2. This example highlights a scenario where the tree has significant width but very little depth. To summarize, the maximum depth of an N-ary tree is determined by the longest path from the root to any leaf. The problem includes constraints to guide your solution. For example, the tree can have up to 10,000 nodes, and its depth can reach up to 1,000. If the tree is empty, meaning the root is null, the depth is 0. On the other hand, if the tree contains only a single node, the depth is 1. Lastly, you might encounter extreme cases, such as a tree with a single branch almost reaching the maximum depth or a very wide tree with no significant depth. These constraints and edge cases will help you design a robust solution. To solve the problem of determining the maximum depth of an N-ary tree, we need to figure out the longest path from the root node to any leaf node. One effective approach is using recursive depth-first search, or DFS. This method involves traversing the tree recursively, calculating the maximum depth of each node's children, and adding 1 to account for the current node itself. The intuition behind this is that recursion naturally follows a depth-first traversal, so it's a straightforward way to compute depth at each level. The steps are simple. If the root is null, the tree is empty, so the depth is 0. If a node has no children, we return 1 since we're at a leaf node. For nodes with children, we calculate the depths of all child nodes recursively, and the maximum depth of those children, plus 1, gives us the depth for that node. In terms of complexity, the time complexity is O, n, because every node is visited exactly once, and the space complexity is O, h, or h is the height of the tree, due to the recursion stack usage. Another way to solve this problem is through iterative depth-first search. Instead of relying on recursion, we use a stack to simulate the depth-first traversal manually. Each entry in the stack keeps track of a node and its current depth. This approach avoids the issues of recursion and gives us explicit control over the traversal process. Here's how it works. First, we initialize a stack with the root node and a depth of 1. Then, as we traverse the tree, we update the maximum depth whenever we encounter a new node. For every node, we push its children onto the stack, assigning them an updated depth value. Once the traversal is complete, the maximum depth encountered gives us our result. the time complexity remains O, n, since every node is processed exactly once, and the space complexity is O, h, where h is the maximum depth of the tree, as that determines the stack size. We can also use breadth-first search, or BFS, to determine the maximum depth. This approach involves level-order traversal of the tree using a queue. BFS processes nodes level by level, which makes it naturally suited for depth computation. The idea is to track the depth by incrementing a counter each time we move to a new level. Here's how it works. We start by initializing a queue with the root node and a depth of 1. For each level, we process all the nodes currently in the queue, enqueue their children, and increase the depth counter as we progress to the next level. When the queue is empty, meaning we've processed all levels of the tree, the depth counter gives us the maximum depth. The time complexity is O, n, as each node is visited once, and the space complexity is O, w, where w is the maximum width of the tree, reflecting the largest number of nodes in the queue at any given time. Out of these approaches, the recursive DFS method is our chosen strategy. It stands out for its simplicity and efficiency. The recursive solution is concise and aligns closely with the problem's definition. The depth of a node is 1 plus the maximum depth of its children. With a time complexity of O, n, and a space complexity of O, h, it performs well for most tree structures. This approach also aligns intuitively with how we think about tree depth. While iterative methods, like DFS or BFS, avoid recursion and may be safer for extremely deep trees to prevent stack overflow, they require additional data structures, like stacks or queues, which can add complexity to the implementation. BFS, for instance, is a good alternative when the tree's maximum width is less than its height, but it's less intuitive for depth computation. In contrast, recursive DFS strikes the perfect balance between simplicity, clarity, and efficiency, making it the ideal choice for this problem. The problem at hand is to find the maximum depth of an N-ary tree. Depth is defined as the longest path from the root node to any leaf node. In an N-ary tree, each node can have 0 or more child nodes. For this problem, we are guaranteed that the tree is non-empty, meaning it will always have at least a root node. The root node may or may not have children. To solve this, we are using a recursive depth-first search approach. The first step is to handle the base case, if the root node is null, which is already guaranteed not to happen, or if the root node has no children, in which case the depth is simply 1. Next, we handle the recursive traversal. If the root node has children, we recursively calculate the depth of each child subtree. This means that for each child, the function will call itself to determine the depth of that subtree. Once the depths of all the child subtrees are calculated, the maximum depth of the tree rooted at the current node is determined by adding 1 to the maximum depth among all its child subtrees. The addition of 1 accounts for the current root node itself. For edge cases, if the tree consists of only a single node with no children, the depth is simply 1. Similarly, trees with varying numbers of children at different levels are naturally handled by this recursive approach. This solution relies on the principles of recursion. It breaks the problem into smaller subproblems, computes the depth of each child subtree, and combines these results. The algorithm is efficient, visiting each node exactly once, resulting in a time complexity of O, n, where n is the total number of nodes. Space complexity is O, h, where h is the height of the tree, as this is the maximum size of the recursion stack in the worst case. To implement this algorithm, we rely on 2 key data structures, the tree node and the recursion stack. Each tree node stores its value and a list of child nodes, which represent the hierarchical structure of an N-ary tree. During the depth-first traversal, the recursion stack keeps track of function calls, allowing us to navigate back up the tree. The Python implementation begins with a node class, which initializes the value in children for each node. The maxDepth function starts by checking if the root node is null. If it is, the function returns 0, though this scenario is already ruled out by the problem's constraints. If the root node has no children, the function returns 1, as the depth is just the root itself. In the recursive case, the function computes the depth of each subtree rooted at the children of the current node. Using list comprehension, we create a list of depths by calling maxDepth on each child node. Finally, the maximum depth of the current subtree is calculated by adding 1 to the maximum value in the list of child depths. This additional 1 accounts for the current node's level. To better understand this, let's walk through an example. Consider an N-ary tree with root node 1, which has 3 children, nodes 2, 3, and 4. Node 3, in turn, has 2 children, nodes 5 and 6. Starting at the root, we call max depth on each child. For node 2, since it has no children, its depth is 1. For node 3, we call max depth on its children, nodes 5 and 6. As both nodes 5 and 6 have no children, their depths are 1. The depth of node 3 is then 1 plus the maximum of 1 and 1, which equals 2. For node 4, as it has no children, its depth is 1. Combining these results, the depth of the root node is 1 plus the maximum of 1, 2, and 1, which equals 3. Thus, the maximum depth of this tree is 3. From this example, we can see that the recursive traversal ensures all nodes are visited, and the depth of each subtree is computed accurately. The use of list comprehension allows for efficient calculation of child depths in a single step, while the max function combines these depths to determine the maximum depth at each level. Although this algorithm is both time and space efficient, there are potential optimizations. For instance, memoization could be used to avoid redundant computations in cases where multiple paths lead to overlapping subtrees. However, in this specific problem, the tree structure does not overlap, so memoization is unnecessary. The solution is already optimal for the given constraints. In scenarios where the tree is extremely deep, recursion may lead to a stack overflow due to Python's default recursion limit. While the limit can be adjusted, an alternative approach is to use an iterative algorithm to avoid this issue entirely. Iterative solutions simulate the recursion stack with an explicit stack data structure, ensuring the algorithm can handle even the deepest trees. This modification is not typically required for the standard problem but can be considered in edge cases where extreme depth is a concern. This implementation solves the LeetCode problem maximum depth of N-ary tree using a recursive depth-first search (DFS) approach. Let's break it down step by step. First, we define the node class that represents a node in the N-ary tree. Each node has 2 attributes: val, the value of the node, and children, a list of its child nodes. If no children are provided during node creation, we initialize it to an empty list. Next, we implement the maxDepth function in the solution class. The maxDepth function takes the root of the tree as input and returns the maximum depth of the tree. 1. Base case, if the root is none, tree is empty, we return 0, as there is no depth to calculate. 2. Leaf node case, if the current node has no children, it's a leaf node, its depth is 1. This is because the depth of any leaf node is simply the root to leaf path, which is 1. 3. Recursive depth calculation, for non-leaf nodes, we iterate over each child node and recursively calculate the depth of its subtree. We keep track of the maximum depth among all children using the max function. 4. Combine results, finally, we add 1 to the maximum depth of the children to account for the depth of the current node itself. This approach ensures that we traverse the entire tree, visiting each node exactly once. The time complexity of the solution is O(n), where n is the total number of nodes in the tree, because each node is visited only once. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. In summary, this code correctly computes the maximum depth of an N-ary tree by leveraging the properties of recursion and the divide-and-conquer principle. It handles edge cases like an empty tree in nodes with varying numbers of children, making it a robust and efficient solution. Here, we start with the definition of a node class, which represents a single node in the N-ary tree. Each node has an integer value, val, and a list of children nodes. We define 3 constructors, a no-argument constructor, one that initializes the value, and another that initializes both the value and the list of children. Moving to the solution class, we define the maxDepth method, which calculates the maximum depth of the tree. The method begins by checking if the root node is null. If it is, the tree is empty, so we return a depth of 0. Next, we handle the case where the root node has no children, meaning it's a leaf node. In this scenario, the depth of the tree is 1, as there's only the root itself. If the node does have children, we initialize a variable, maxChildDepth, to 0. This variable will keep track of the maximum depth among all the child nodes. Using a for each loop, we iterate through each child of the current node and recursively call the maxDepth method. For each child, we calculate its depth and update max child depth to hold the maximum value observed so far. Finally, we add 1 to max child depth to account for the depth of the current node itself and return this value. This ensures that the depth calculation includes all levels of the tree, starting from the root down to the deepest leaf. To start, let's consider the simplest case, a tree with just a single node. Here, the input is a root node with the value 1 and no children. The max depth function is called with this node as the input. First, we check if the root is null, which it isn't, so we proceed. Next, we check if the root has any children. Since it doesn't, the function simply returns 1, indicating that the maximum depth of this tree is 1. This makes sense because with only one node, the depth is exactly 1 level. The final output for this example is 1. Now, let's examine a more complex tree with multiple levels. The root node has the value 1 and 3 children, nodes 2, 3, and 4. Node 3 also has its own children, nodes 5 and 6. The max depth function begins by checking if the root is null, which it isn't, so we continue. Since the root has children, we initialize a variable max_child_depth to 0. We then iterate over each child of the root. For the first child, node 2, we call maxDepth. It has no children, so the function returns 1, and max_child_depth is updated to 1. Next, we move to node 3. Since node 3 has children, we recursively calculate the maximum depth of its subtree. At this point, max_child_depth for node 3 is initialized to 0, and we begin iterating over its children. For node 3, the first child is node 5. The maxDepth function is called with node 5, which has no children, so it returns 1. This updates the max_child_depth for node 3 to 1. The second child of node 3 is node 6. Similarly, maxDepth is called with node 6, and since it also has no children, the function returns 1. The max_child_depth for node 3 remains 1 because the maximum of 1 and 1 is still 1. At this point, the maximum depth of node 3's subtree is determined to be 2, which is calculated as max_child_depth plus 1. The max_child_depth for the root node is then updated to 2, as this is the greater value between the depths of node 2 and node 3. Finally, we process the last child of the root, node 4. Since node 4 has no children, the maxDepth function returns 1, and the max_child_depth for the root remains 2, which is the maximum of 2 and 1. The maximum depth of the entire tree is therefore 3, calculated as max_child_depth plus 1. The final output for this example is 3. Finally, let's consider the case of an empty tree. Here, the input has no root node, so root is equal to none. The maxDepth function is called with this input. The very first condition in the function checks if the root is null. Since it is, the function immediately returns 0. This result makes sense because an empty tree has no levels, so its depth is 0. The final output for this example is 0. The time complexity of this solution is O(n), where n represents the total number of nodes in the N-ary tree. This makes sense because the algorithm needs to visit every node exactly once. The depth-first recursion ensures that we traverse the entire tree, starting from the root and then moving to each child node. At each node, we loop through its children, but it's important to note that every child across the entire tree is visited only once during the traversal. This means the total work done is proportional to the number of nodes, and additionally, the operations performed at each node, such as checking for null values or comparing depths, are constant. Therefore, when summed up across all n nodes, the overall time complexity is O(n). Now, let's consider the space complexity, which is O(h), where h is the maximum depth of the N-ary tree. This arises from the recursion stack used during the depth-first traversal. The depth of this stack corresponds to the depth of the current node being processed. In the worst-case scenario, which occurs in a skew tree where each node has only one child, the recursion stack can grow to the full height of the tree, which is h. In a more balanced tree, even though there are more children at each node, the recursion depth still depends on the height of the tree, not the number of children. Since no additional data structures are used beyond this stack, the total space complexity is determined by the maximum depth, resulting in O(h). Let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, the tree contains only one node, the root. Here, the algorithm performs a single operation and terminates, giving O(1) for both time and space complexities. In the average case, we consider a balanced tree with a branching factor of k and height h. The total number of nodes, n, is approximately k to the power of h1/k1, and the algorithm still visits all n nodes, leading to O(n) time complexity. The space complexity remains O(h), as it depends on the tree's height. In the worst case, we have a highly skewed tree that resembles a linked list, where the time complexity is O(n), and the space complexity is O(h), with h equal to n. Comparing this to a brute force approach that calculates subtree depths independently, which could take O(n²). In some cases, our optimized solution avoids redundant computations by using a single depth-first traversal, ensuring O(n) time complexity. To formally prove the big O bounds, let's start with the time complexity. Each node in the tree is visited exactly once, and the operations at each node, such as checking its children or comparing depths, are constant. Since there are n nodes, the total work performed is O(n). For space complexity, the maximum space used corresponds to the depth of recursive calls, which is proportional to the height of the tree, h. This means the recursion stack grows to a maximum of h frames, resulting in O(h) space complexity. These proofs confirm that the time complexity is O(n), and the space complexity is O(h), as derived earlier. When working with this problem, there are a few common mistakes you should watch out for. One of the most frequent is confusing BFS and DFS when implementing your solution. If you're using BFS, remember that depth is determined by the number of levels processed, not the total number of nodes visited. Misinterpreting this can lead to incorrect results. Another common pitfall is failing to handle null or edge cases. For example, not checking for an empty tree or a tree with only one node can lead to runtime errors or incorrect depth calculations. Additionally, it's important to account for the varying number of child nodes in an N-ary tree. Hardcoding the iteration logic based on a fixed number of children per node will cause issues, as each node can have a different number of children. Finally, be cautious with recursive DFS solutions, especially for very deep trees. If the tree's depth approaches 10,000, the recursion stack could exceed system limits and cause your program to crash. Ensuring your solution handles these cases robustly is key to solving the problem effectively. Another mistake to avoid is incorrectly summing the depths of child nodes instead of finding the maximum depth. Since depth is defined as the longest path from the root to a leaf node, summing depths will lead to incorrect calculations. Beyond common mistakes, there are also some key insights to keep in mind for interviews. Always clarify the tree's structure with your interviewer. Confirm whether it's binary or N-ary and how the children are represented. This could be a list, array, or another data structure. You should also understand when to use an iterative solution, like BFS, over a recursive one. Iterative methods are often safer for very deep trees as they avoid recursion stack limits. Be prepared to explain this trade-off. Additionally, make sure to mention edge cases, such as empty trees, single-node trees, or highly unbalanced ones, to show that you're thinking comprehensively. Lastly, be ready to discuss optimization. While the time complexity for both BFS and DFS is O(n), you might be asked about memory usage, such as the stack size for DFS versus the queue size for BFS. Finally, let's connect this problem to related ones and explore alternative approaches. Some similar problems include LeetCode 104, which involves finding the maximum depth of a binary tree, and LeetCode 110, which focuses on determining whether a binary tree is balanced. Other examples include LeetCode 111 for finding the minimum depth of a binary tree and LeetCode 429, which covers level order traversal in an N-ary tree. In terms of solving approaches, there are three main strategies to consider. The first is recursive DFS, where you traverse each path recursively and calculate the depth of each subtree, returning the maximum depth. This method is simple and elegant but risks stack overflow for very deep trees. Alternatively, iterative BFS uses a queue to process nodes level by level, incrementing the depth at each level. While this approach avoids recursion depth issues, it does require additional memory for the queue. Lastly, a hybrid DFS with an explicit stack can simulate recursion iteratively while keeping track of depth. This approach combines the logic of DFS with iterative safety, but it can be more complex to implement. Understanding these options and their trade-offs will help you choose the best approach for the problem at hand. Great work! To recap, we solved the problem maximum depth of N-ary tree by exploring recursion and BFS approaches. We highlighted the importance of tree traversal techniques and their applications. Don't forget to practice, and stay tuned for more tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!